Alrighty guys, I'm going to make a couple videos here for you for when I'm out tomorrow. And this one is in case you missed class on Friday where we practiced multiplying radicals. We had been practicing simplifying radicals. For instance, square root of 24. If I break up 24, I know 6 times 4 is 24. And I picked those particular factors because 4 is a perfect square. I can take the square root of 4, and the square root of 4 is just 2. So when I take the square root of 4, it's 2, but the 6 not being a perfect square, I end up leaving it underneath the square root. Now, if you remember, the way we started this is once we found the perfect square, in order to show you that I was going to take the square root of the perfect square. We said that since this is all multiplication, I can break the product up and give each one of those its own square root. So I took that product of 6 times 4 underneath the square root. I broke it up still as a product, but where each one had its own square root. And then I took the square root of 4, which is just 2, and did not take the square root of 6. And if you plug those into the calculator, this one, the square root of 24, and 2 square root of 6, you would get the same value. They're just equivalent statements where 2 square root of 6 is simplified, square root of 24 is not. But what I want you to focus on here is the way I broke the product up so that each one of those factors got its own square root. Well, if I'm multiplying square roots, I'm going to do the reverse. So if I can split a product up and give each one of them their own square root, I can also put those back together. So square root of 5 times square root of 8, I can put them under one radical and make it square root of 5 times 8, which is square root of 40. But then 40 is a square root that can be simplified. If you start factoring it and you say 40 is 4 times 10, you don't need to go any farther because 4 is a perfect square. I can take its square root. And 10, its only factors are 2 and 5. Neither one of those is a square root. So I am going to break this up into the square root of 4 times 10. Take the square root of the 4, which is just 2, and simplify it to 2 square root of 10. But then we talked about on Friday how if we're going to end up, after we multiply those two numbers, breaking the two numbers down to look for a perfect square, it might be simpler to break the numbers down into their factors instead of multiplying them. So I put the 7 and the 21 under one square root. But now if I start factoring 21 is 7 times 3. And that is useful because if I see that, that's 7 squared underneath the square root. And we know that the square root of anything squared is just itself because squares and square roots cancel each other out. So the square root of 7 squared, or the square root of any number squared, is just itself. So when I end up with that square root of 7 squared underneath the square root, it's essentially equivalent to the square root of 49, but the square root of 7 squared is just 7, and the 3 stays underneath the square root. So rather than build the number up by multiplying 7 times 21, I broke the 21 down into 7 times 3 to see if there were any perfect squares, and indeed there were, because 7 times 7 is 7 squared, which of course is a perfect square. So on this one, if I'm multiplying square root of 3 times square root of 15, I can put the 3 and the 15 together, and then I'm going to break the 15 up into its factors, 3 times 5, so it's 3 times 3 times 5, and there's my 3 squared, square root of 3 squared times 5, but I know the square root of 3 squared is just 3, so 3 square root of 5. When you have coefficients outside the square root, remember that multiplication is commutative, meaning that the order in which I multiply numbers doesn't matter. So if I have 5 times 8, it's going to give me the same answer as 8 times 5. So when I see something like this, I don't have to do it this way, but it might be easier to reorganize so that the numbers are together and the square roots are together. Because again, multiplication is commutative and order doesn't matter. And that helps me to see that I can do the 5 times 4, which is just 20. There's no square root, so I'm just multiplying two numbers. And then the 10 times 2 underneath 1 square root. I'm going to break the 10 up into 5 times 2. So 20 times the square root of 5 times 2. That's that 10. But then there's the times 2. And that gives me the 2 squared. So equals 20 times the square root of 5 times 2 squared. But the square root of anything squared is itself. So this is just 2. Remember, square root of 2 squared is just 2. So that's what I'm doing right here. I'm taking the square root of 2 squared, just 2. It's all multiplication. So 2 times 20 times square root of 5, or 40 square root of 5. Okay. This one right here, it turns out to be a little bit interesting because when I end up with no square root left in the answer. If I do 2 times 5 times square root of 7 times square root of 7, that's 10 times the square root of 7 squared, because the 7 times 7 is 7 squared. The square root of anything squared is itself, so this is just 7, and 10 times 7 is 70. Because I ended up with a perfect square, there was no square root left. So that essentially is a summary of Friday's lesson, and you do have an assignment to go with it. If you have, just really quickly, if you have one that has no number out front, remember there's that implied 1. So it's 9 times 1 times square root of 14 times square root of 10, or 9 square root of 7 times 2 for 14, 5 times 2 for 10, and here's our square. So 9 times the square root of 7 times 5 times 2 squared. I'm going to take the square root of 2 squared, which is just 2. 2 times 9 is 18. The 7 and the 5, I'm just going to put them back together as 35, since 7 times 5 is 35. So anyway, there's an assignment in Canvas from Friday, which is dated today for you to work on. Just remember that you're not going to plug these into the calculator and get that decimal, because we are simplifying square roots. We're looking for exact answers here. So we're going to end up with a whole number and a number underneath the square root, unless that square root resolves itself like it did in this example. All right. Talk to you later.